Hello and welcome to the 1.03 Solids, Liquids, and Gases screencast. This is the second in my series for 1.03. I'm Mrs. Willie and let's get going. A state of matter is a distinct form in which matter exists at a certain temperature and pressure. There are four subcategories of naturally occurring matter. We're only going to focus on the three. Solids, which are tightly packed particles with a vibrational energy, which means they have a small amount of energy. They are moving, they aren't completely stopped, but they're very tightly packed together. So those particles we spoke about in the last video, the atoms are tightly packed together in a solid, or the formula units are tightly packed together in a solid, or the molecules are tightly packed together in the solid state. They have a definite shape and volume, strong interparticular forces, which means the forces between the atoms or between the formula units or between the molecules are very strong, and they are not compressible, which means you cannot get them to fit into a smaller volume. Liquids are freer flowing particles, have more movement, they've absorbed some energy. They have an indefinite shape, which means they depend on their container, and they have weaker and particular forces. They're not as tightly bound together, so they have a little bit more movement, and they're not compressible. Gases are free-flowing particles, lots of movement, highly energetic, have an indefinite shape. They depend on their container. Weakest of the three in their interparticular forces, and they are compressible, which means they can be put into a smaller volume. So we're going to focus a little bit on gases here. The properties of gases have been modeled through experimentation and can be explained using the kinetic molecular theory. The kinetic molecular theory has four postulates. The forces between gases very weak, and the particles of a gas are so small compared with the distances between them that the volume can be assumed to be zero. Therefore, the shape and volume of a gas are entirely determined by their container. This is what explains why gases are compressible. It can be moved from a container with a large volume to a container with a smaller volume without changing the amount of the gas particles present. Gas particles are in constant motion, and their collisions with the container are the cause of the pressure exerted by the gas. Gas particles are spread far apart and move very rapidly. Therefore, the forces between them are very weak. Gas particles are assumed to exert no forces on each other. The particles do not repel or attract to one another. Therefore, the forces between gas particles are very weak. The average kinetic energy of a sample of a gas is directly proportional to the Kelvin temperature, which is just a unit for temperature measurement of a gas. So the higher the Kelvin temperature, the more kinetic energy it has, the faster those gas particles are moved. The lower the Kelvin temperature, they're still highly energetic, but the slower they will move. Some chemical formulas have state signifiers as a subscript at the end, in the parentheses at the end. These state signifiers inform you the state of matter of the substance. So a solid sample of iron would have parentheses S on the end. That's how you know that it is solid. A liquid sample of water would have L in parentheses at the end, so you would know to draw the particles a little bit further apart with a little bit more energy. And the gas would have a small g in the parentheses at the end, so therefore you would know to draw those particles very far apart because they're highly energetic. An aqueous sample is in parentheses AQ, so if you have calcium hydroxide, like I do in this example, that means that the calcium hydroxide formula unit is mixed in with water. And so AQ, whenever I see AQ, that means I know I have water molecules and whatever the formula unit or the molecule, the other molecule is mixed together. So whenever I see AQ, I have to think to myself, water is in that solution. So this is the end of the States of Matter screencast. See you in the next one.